Okay, so I think we're ready to start with the next session. From now until lunchtime, we will be talking about symbolic AI. We already heard that a bit in the first talk, but now we're really going to jump into the limits of possibilities of symbolic AI. First of all, my name is not Agata Ciabattoni. I'm Magdalena Ortiz, also from TU Wien, and I'm jumping in for my colleague Agata, who unfortunately couldn't moderate the session today. Also, I hope my voice, I was just sick and my voice is not in the best shape. But anyway, let's get started. It's my great pleasure to introduce Thomas Eiter. Please. Go. I lost it. Thomas is the head of the Institute of Logic and Computation. He's not the institute, but almost. No. The head of the Institute of Logic and Computation here at TU Wien. He has been a professor here since 1998. And he has also been doing symbolic AI since then. He's a very, very well-known person in the symbolic AI community. He has been in almost every major knowledge representation and symbolic AI conference, board, committee Thomas has been or is a member of. He is a fellow of the ACM, of the European Association for Artificial Intelligence, of the Asia Pacific Association for Artificial Intelligence, of the Austrian Academy of Science. I will not bore you with the long list. He's currently the president of the Association for Logic Programming, and he was president of the Association for Knowledge Representation and Reasoning. So he's really a person that has been at the core of symbolic AI over the last couple of decades. So, Thomas, the floor is of yours. Thank you very much.
Okay. Thank you very much, Magdalena, for this very kind introduction and for the possibility to speak here at this workshop about paradigm shifts in computer science, possibly through AI or not. So I should now, in the next half hour, just talk a bit about symbolic AI, what it can do and what it cannot do. You already heard a historical introduction to AI. The AI had a quite mixed history. There is divergent opinions on the history of AI, I have to say, because I would not agree to all of the statements in the previous talk, but maybe I can come back to that. Still, I mean, it's even though Magdalena said we should jump right into the possibilities and impossibilities of symbolic AI, still to recall some influential ideas. So even though some of them already have been mentioned in the previous session. So what symbolic AI is about, or how people were looking at symbolic AI. And here we see Marvin Minsky, who said it's the term for a collection of all methods in AI research that are based on high level, so symbolic, and importantly, human readable representations of problem, logic, and search. And another quote here is from John McCarthy. So we also heard about that McCarthy and colleagues teamed up in order to have this famous workshop or conference at Dartmouth, where they needed a name to get funding from the government. So they came up with artificial intelligence, which it sounded quite attractive. And he said it's one path to human level AI. It uses mathematical logic to formalize common sense knowledge, such that common sense problems can be solved by logical reasoning. So McCarthy was deeply convicted that logic and mathematical logic, which had been invented more or less to or pushed forward to give solid foundations to mathematics, can be, so to say, an instrument in order to achieve these goals. We heard already about early hypotheses, so to say, about what can generate intelligence, and in particular Newell and Simon's work has been very influential. So the symbol processing hypothesis, which basically said a physical symbol system, or they wrote, has the necessary, they said necessary means, and sufficient means for general intelligent action. So according to this hypothesis, there is no real intelligence unless we have a physical symbol system where we manipulate symbols. And later then, Leonard and Feigenbaum in the 80s came up with the knowledge principle, so that the system exhibits intelligent understanding and action at a high level of competence, primarily because of specific knowledge that can bring to bear. So we have concepts, facts, representation, and so on. So important again is that we have models, that we have abstract concepts that actually can be manipulated and can be reasoned about. No? Maybe perhaps less known these days, but still something which had quite some influence, and also on development of programming languages, and other ones in the area of AI, was the frame idea that Minsky had. So more or less that one has something like a prototypical representation of a situation in a structure that he called frame. And when it comes to a particular situation or instance, then we take that frame and instantiate it. So that it could be, as we see it here, for example, well, it could be a car. You have a general representation of a car, and then when it comes to a particular car, like a car with a license plate and so on, then you would just instantiate that frame. For some of you this sounds like object-oriented programming, then yes. So the ideas actually were around at the same time, and systems were built actually manipulating these frames. There were some drawbacks because one could not really reason about these systems. The semantics was very much procedural at the time, which was not very good, because one could not really make good predictions about the behavior of these systems. Another important development was conceptual graphs in the 70s and in the 80s, and a number of conceptual graph systems have been built. So you see here a number of them. Again, there was an issue of semantics to some extent, because on the one hand, they tried to use logic and concepts from logic to give a semantics to these systems, but also had operational, procedural elements in that. And that again was an issue then when one wanted to reason about these systems. Later then, systems like KL1 and relatives, like classic, back and so on, were developed, which were better in these respects. And actually they gave rise to description logics then in the end, which were firmly grounded on logic and logical languages and reasoning methods and tools, so that they have the advantage of a very clear, precise semantics. There's no debate about the semantics of such systems. Most of you will never have heard about that, but that's so-called agent-oriented programming. So proposed already 30 years ago by Schoem in his vision that we have a computational framework that is based on societal computation and interaction of agents in a system where one programs agents directly, where notions like beliefs, intentions, and goals, later then agent architectures, we heard a bit about the development of agents, have been developed, where these concepts, belief, intention, and goals were also couched into logic-based languages, which is a bit difficult to do, but at least there was research underway. And to use an intentional stance to program machines. And this was thought also as an enrichment and an refinement of object-oriented programming. Now, I mean, what could early systems do that were based on symbolic methods? And well, playing games, as we heard, was always up on the agenda. And I mean, Turing himself wrote programs for playing chess at a time where there was no hardware to execute these programs. One has to mention also other games like checkers, which are a bit easier, simpler, so to say, than chess. And the ambition was to beat the best human players. So the systems that were developed in the 60s, 70s did a decent job, but actually the goal to really be at the level of the top human players was not achieved at that time. Theory improving also was early on considered. Well, it is close to mathematical logic. If you are able to axiomatize a certain mathematical field theory, then you might use a logic reasoning engine. in order to, on the one hand, find proofs for existing theorems, but also to find new proofs, new theorems. And that, to some extent, for a geometric reasoning engine was achieved was in the 60s, so to say. Language, of course, is a very important topic, natural language. And of course, an important element of intelligence. And so, of course, researchers also tried to do something in that direction. I just want to mention ELIZA, which was not thought of as a deep natural language processing system. It was more just to do some kind of simple transformations of input to output. The astonishing thing was how people reacted to that. We see something similar nowadays with all these large language models and the chatbots on top, so like ChatGPT, where people, of course, I mean, the level of sophistication nowadays is much larger, but still, so that people attribute then too much, perhaps, weight into answers that come from such a chatbot. Or in limited domains, to be able to understand questions and give answers, like Winograd was doing. Planning, as we heard, is also an important problem. Early on, McCarthy, for example, was giving this as for a motivation. And there was a landmark system, and that is called STRIPS, that also made it then into programming robots. So you see a Shaky, the robot that was developed at the Stanford Research Institute in the late 70s, beginning of the 80s. Even though, well, the robot actually needed quite some time to come up with conclusions, so that they said the robot always will be safe if it tries to cross the road, because the reasoning time to figure out whether it should cross or not will be so long that he will never be endangered. So that was a bit of an issue. We heard about expert systems, which made it into a boom in the 80s, filling large halls of conferences. I was once talking to an organizer of an IJCAI conference, International Joint Conference of AI in Los Angeles in the 80s, and he said he had to meet a stadium in order to be able to have an industrial day because there was so much interest. And we see it similarly nowadays with the boom in AI and especially in machine learning, that is attracts thousands and 10,000s of people. So one could master, as we heard, narrow-minded, so to say, specific problems in an area. These expert systems were around for everything. It was a buzzword. Everybody wanted to develop an expert system, even though for problems that would not have needed an expert system. So I made experience myself. So I was working actually in a Christian Doppler lab. That was a very important activity, initiative of Austrian industries. At that time, Austrian industries had visionary leaders. They set up this Christian Doppler Society for funding research that is application-oriented. In the end, we'll have applications, but should have applications on a long horizon. So I was working in that lab. So that was on expert systems, and actually in that lab we could achieve a number of results that nowadays are widely used after in the long term, not in the short term. So one was using search logic, probabilities, uncertainty measures, and hybrid methods actually to achieve this. So what could such systems not do? And they're still struggling with this. Of course, one issue is vision. Or generally, more generally, if we have sensory input. All of you, if they look at the image on this slide, see there is an animal. This will be a tiger. So if you do a kind of classification, what kind of animal this is. So even for vision systems nowadays, this might be a bit of an issue, because I mean this is partially occluded. We as humans are very good in recognizing this, but this is just evolution. Now those who recognize the tiger and do the appropriate reasoning, tiger is dangerous, they can escape. Those who do not, well, they are eliminated by natural selection. What Symbolic AI cannot do is deeper natural language understanding. We heard also about projects like Hearsay in the 70s. There's many There's been many other attempts of building symbolic models for natural language understanding, but they didn't come up to the expectations. No? Another issue is to deal with exploding search spaces. No? That is something that early AI system could not do. Actually, many of the problems that symbolic AI is dealing with are plagued with intrinsic difficulty, which manifests in the notion of NP hardness. No? So the theory of NP completeness with a unifying field for finding out which problems are easy, which problems are difficult, or we might not have polynomial time algorithms. Still, this is the million-dollar question to solve. Many such problems were around, and at that time, if you said problem is NP hard, this was the kiss of death, because everybody said, put your fingers off, you will never be able to deal with these problems. We know nowadays better, and I will say something about that. No? And, well, one could not go beyond limited tasks. Now, the AI was narrow, was limited to specific tasks and applications. No? Just a remark in that context, so this is what Turing actually was supposing, or proposing in his famous article, is that one should build learning machinery, a learning machine that actually could learn by itself, because sometimes it might be too difficult to program a machine. And he was anticipating the major components that AI systems should have. They should be built on knowledge, they should be able to reason, they should be able to understand language, and most importantly also they should learn and learn by themselves. Now what can AI do nowadays? There have been quite some advances. No? So we have advances in semantic systems and in knowledge graphs, for example, game playing. Actually, there have been quite some advances. No? Solving mathematical problems, verification is a topic where actually strength of the logic-based method manifests. Problems in combinatorial optimization and configuration planning, scheduling, for example, just would fall in that area. We have declarative programming systems which allow to concentrate on the description of solutions rather than on the algorithms behind, even though this paradigm doesn't scale to the level as we would like to have it at this point. And advances in multi-agent systems in various forms, be it auctioning, be it elections, social choice, and so on. Just one important area where there's been quite some advance is querying the web, so to say. So the web actually shows that symbolic method is needed in order to advance our processing of knowledge and information. The usefulness of the web in the end hinges on the idea to add semantics to the data, because data by itself has no meaning. But to process data, to chain data, to use that data, you need semantic descriptions. You need meta information, metadata, etc. And you have to process that in the right way. And symbolic techniques and reasoning techniques are at the core of that. And there is the web ontology language, for example, which caters for this semantic markup in different variations and forms. We had heard about knowledge graphs before. So what is a knowledge graph? Well, Google invented the term. So basically they were resorting back to conceptual graphs which have been invented in the 80s. It was just rebranded. It's a more sexy, attractive name to talk about knowledge graph and not about conceptual graphs. And that's the backbone of semantic reasoning on the web. If you ship queries to the web in order to glue together pieces of information. And beyond that, with ontological reasoning, we have systems that are able to deal on large scale with data like the SNOMED system for classification in medicine. Game playing might be known, or some of the successes might be known to you for sure. So there have been quite some advances on checkers that we mentioned before, so that really one could be at the level of top human players. Deep Blue made it into the press after a long time where nobody heard something about AI, when Deep Blue was defeating Kasparov in this famous tournament in 97. Even though one has to say that the technology was not revolutionary at the time, so it was massive hardware, it was bringing to fruit all of the technology, the search technology and the game tree technology that had been developed before. Libratus pluribus, who heard about Libratus pluribus before in the audience? It's only one person, 2 persons actually heard about that. No? Everybody knows about AlphaGo. No? That made it into the press very prominently, and journalists were coming, interviewing. I'm not mentioning that because that's a combination of search and neural networks. I'm more concentrating on the so to say, more pure, under quotation marks, symbolic AI stuff. Well, that's a program that's playing poker, and poker actually is much more difficult than playing chess. Why that? Well, in chess you have complete information. You see the board. While in poker you don't know the hand of your opponents. And so I mean you have to hypothesize about what would be the hand of your opponent. And actually, then if you are thinking how to play this out, you cannot just divide a game tree into independent subtrees. This doesn't work. So you have to have other techniques, and you have a very huge search space. And there was a breakthrough that was achieved by Thomas Sandholm and his team at Carnegie Mellon, so that they really defeated top world-class poker players in a 1 or 2 weeks tournament. They were playing large number of hands through revolutionary techniques. Later then, actually, the system was furthered to be able to play against multiple players, and noticeably, the power, the consumption, the energy that was needed for doing that was shrinked from a supercomputer. Renting that computer costed $100,000 a day to just conventional hardware. So that means to have clever search techniques, algorithms and methods is very important. Solving mathematical problems. So a milestone was the first time where a difficult open problem was solved, the 4-color theorem, whether you can map a color, whether you can color a map always with 4 colors, such that neighbored areas never have the same color. So this was a very long time open question, was solved with the use of computers then in the end. I mentioned checkers before. Actually, that game is solved in the sense of that we know now what is an optimal strategy. We don't know it for chess. We don't know it for Go. So I mean, you have all these Go-playing programs, but we still don't know whether there's a winning strategy, so that you, as a player, have a way to win the game, or at least not to lose the game. But we know it for checkers. Kepler's conjecture has been open for centuries also. So how to staple balls in a volume optimal way. Or most recently, so this year, Pythagorean triple problem. So you know, a square plus b square is c square. Now you would like to color them, and you should do so now so that never, Stefan knows it better than me, that all the 3 with the same color have the same color, where you have 2 colors only, red and blue. So this has been open also for quite some time, and using SAT technology, so proof technology, in a clever way, this problem has been solved just a couple of months ago. And you see here actually the programs and the space that was needed for doing this is huge, but still it's manageable to do that in the end. We heard about verification. Earlier I mentioned that, and verification always has been an intriguing issue, whether a program or a device would do the right thing. And we know that in general this is an undecidable problem. So you would say there's no way to do something, but under restrictions, and that might work out in practice, it is still a problem that can be solved. And actually, techniques that have been developed in the area of cyber-physical systems, in particular built on temporal logic, then could be used for that. And the landmark was when Ed Clark, so in the mid-90s, could debug, so to say, the Pentium or a processor who had a bug and actually find the reason. And not only that, with his methods, he also could show that there were some other flaws that were hidden and not known at the time. That actually furthered the interest in verification. And it's quite useful for proving correctness of specification. This has been taken up not only by hardware and chip producers, but also by the software industry. So like Amazon Web Services, Microsoft, and so on, aim at verifying certain pieces of software that they are producing. It has big potential for security, so there's also quite research underway. And more recently, people are also looking into logical synthesis. This means to have correctness by design. You describe what you want, and then in the end that the system is assembled that actually should have these possibilities. Another area where methods from logic and search are quite useful is combinatorial optimization. If it comes to solve big optimization problems, where in combination with heuristics we have the possibility to produce on the one hand, say schedules for terminals optimizations, but also in other areas, like in configuration and scheduling. So configuration is a very important problem. We have a bunch of configuration experts in the room here now who have been working on that problem for more than 30 years, and large-scale configuration problems could be, I mean, to nowadays perhaps, well, less of an interest, but if you were configuring the phones of a big company that has thousands of phones, or if you have a railway system where security devices have to be configured. It could be plants and so on at a large scale. To deal with that, you need respective methods, and methods from logic and search turned out to be quite useful. Scheduling is a bit more intriguing problem because we have to take time into account. We have to arrange things in an order. We have to respect deadlines, start times, and so on. This is important for job processing, for tournaments, and all kinds of things. Just a word on that, why in particular to use symbolic methods can pay off here. Learning is of limited value, or has some limited value in these applications, because often the formulations are ad hoc. We have hard constraints that have to be obeyed. There is data which is missing, and very often we have to deal with changes, so that these schedules will have to be changed on the fly. And this is an issue where learning methods actually struggle. So what's AI missing? So AI is missing still quite a bit, and to some of these areas, then I will say that symbolic methods may contribute something. So from a cognitive perspective, quite a bit. So the methods and tools that we have, systems that we have today, they lack deeper real-world reasoning. So this has been acknowledged, and if you use systems like ChatGPT and relatives, you will realize that. So the kind of inferences that are made there are quite shallow. There are issues of abstraction, and generalization, as it's very often called. And, well, an evergreen, so to speak, is common sense. How to build systems that are able to deal with inferences and with knowledge that's so trivial to us that we even would not mention it. So like objects fall down by gravity, a selfish person will never share its cookie. Behind is a transitive relation and things like that. From a technological perspective, there is still also quite some bit. So we will certainly hear something more about that in other presentations. So especially I will concentrate here on explainability and just say a bit about that. But there is also a social perspective, where actually the logic-based methods can contribute quite a bit. Namely, when it comes to interaction, and when it comes to especially to norms and ethics. Just for abstraction, just an experiment. So maybe you know the mutilated chessboard problem. Who knows that problem? A couple of people. So a classic, now you take this chessboard, you chop off the opposite corners. Now the question, is it possible to place dominoes of size 2? So basically black-white domino, so to cover all the remaining squares. No? So what's the answer? No? So if you say no, no, so no, you're a quick thinker. No? Here is an example where one tries to do it. It's not so good well visible, but actually it's not possible to do that. No? Well, if you ask ChatGPT, it gives the right answer. No, you cannot do it. Why that? Well, you will have more black squares than white squares. No? And we are domino as one black, one white, so it's not possible to do that. So ChatGPT is perfectly right with that, and it gives a nice explanation. But if you ask, okay, if the board has a size different from 8, is it then possible? And it says, oh yes, no? And then it gives you an example now of a board which actually is not. So I mean, it has difficulties with doing that. No? So that's an issue with that. Or problem solving. No? So I just yesterday asked about, no? A car is traveling from a city A to city B at a distance of 50 kilometers. And so on, at a certain speed. Another car now starts 10 minutes later and travels, blah, blah, blah. Now, how far is that car going? Okay. Well, it's actually, it answers so the known facts. No? And then it says, we are tasked to blah, blah, blah. Actually, I mean, it's not asked that. No? So it should answer the question, and that would be it's going 50 kilometers because it's traveling from A to B. No? But the system understands. No? That actually you want to know how far it can get in the time that the other car is traveling. So this is a misunderstanding. So it's important to have a clear context, that these systems are able to listen, to understand questions in order to give the right answer. Still, the systems fail on more involved problems. And there are nice examples as puzzles that we gave out at the Vienna Ball of Science, where the system gave an utterly wrong solution to that problem. No? So symbolic AI techniques are instrumental for deeper world reasoning because it build on methods where actually it's possible to chain inferences in a sound way and also to respect very important notions like causality. So I will not talk much about causality here because that would one would have to devote a whole lecture on that. It's still an issue and something that many of the existing systems cannot deal with well. Common sense I was already mentioning. From a historical perspective, there were attempts in the 80s to formalize common sense and to build common sense systems. Like Leonard, whom I already was mentioning, was building the Psych system, which was a large system, encyclopedic system for answering questions based on common sense. It didn't really fulfill its expectations. There is still a company around. One can use OpenPsych, and maybe by other models, but this is still an open issue. To have verified systems, so this is, everybody talks about verified systems, that we have systems where we have provable properties and so on. But if you want to verify systems, then we need a formal specification. Only if you have a formal specification, you can verify a system. And for that, you will need some kind of formal languages that are related to logic or logic-based languages. Ethical systems, well, for us to deal with norms and rules is very important. And norms and rules are symbolic concepts. They might involve quantities and other things, but these are symbolic concepts. And there is streams, areas in logic and knowledge representation which are dealing with these aspects. And so it has quite something to offer for that. To model epistemic and mental states. If we want to have interaction with a human or another agent, then we have to make or will make assumption about what actually does the other agent know. And importantly, what are his or her intentions if you have a communication. It's easy to trick ChatGPT and other systems by hiding, masquerading your intentions, what you really want. And the system might not be able to figure this out because it's not able to find out your intentions. If you try to distill bad words or bad language from the system, if you try to do that straight, it will refuse. But if you say, well, you see, as a colleague told me, I have to write the play. No, there is a very fishy bad character. No, so I would need to write in the language that person is using, and then I mean you get all the bad words. No, you would better not have heard. No, and explainability. So there is a need for explainability and the movement, explainable AI. That just arose because many of the systems that are in use are not transparent. So we need for that actually a model of a system, and that involves also to have some structure and not just a very big black box, that also has some form of modularity and that we can reason from and reason about the model. That we can ask questions like why did something happen, or also why did something not happen? No? Just briefly for explainability, how much time do I have? 4 minutes? 2 minutes. Okay, I mean, so that's, well, we see here now you have many times systems where you have an input and you have an output, but you don't know how this output actually is coming about. And the last one, so in particular, if you want to get a mortgage, you give your data and then the system says no, you want to know why. And actually by the GDPR and other guidelines, this is nowadays compulsory to do that. No? Building trust is very important. No? So this is something that perhaps I do not have to explain much about. But symbolic AI techniques have quite something to offer in that regard, because one needs formal frameworks, guarantees, and warranted behavior now of systems. And there is methods and tools available that have been developed by logic. So for time reasons, I cannot go into the details of that here. But there are a host of techniques that tries to get around this problem by using different methods, other neural networks for explaining neural networks, have attention maps, hot maps, and things like that. But in a logic-based approach, we would like to model the respective system in a logical system and then distill logical explanations out of that. No? There are quite some benefits for this approach that will provide us with a range of explanations, actually, that we can obtain. There is strong points of symbolic AI that can be exploited for that. We have correctness by, so to say, the intrinsic idea of logic, so that we have sound reasoning. In some cases also that we have complete reasoning depending on the methods, that we have transparency, that we have transferability, because by itself, logic, when we are modeling certain domains, now we are already at the level of abstraction, in particular, if we are using predicate languages. No? So we can exploit a number of reasoning techniques that cater for different capabilities that are needed for that. And there is a rich landscape of tools available that has been developed over the years. SAT solvers I already mentioned. Well, SAT is an NP-complete problem, but we are able to deal with very large instances of SAT, with millions of variables and clauses. This doesn't come by itself. It's because one can exploit structure, and there is a lot of engineering, algorithmic engineering also, which is needed for that. And we can use reasoning engines also in proof systems for analysis in very astonishing contexts. There are quite some issues that symbolic AI is suffering from. Computational cost is the most pressing one. Nothing comes for free. But there is an analogy, so to say, to this Kahneman's model, which many of you might have heard of. System 1 is for fast, intuitive thinking. System 2 is for deliberate thinking and tasks like planning. And that actually takes also for us as humans more time. So it's no wonder, so to speak, that such reasoning capabilities take more time. There is the issue of conceptualization. We need to build the knowledge bases. We have to find a vocabulary of the domain. And the interfacing is an issue. Coping with irrational and illogical behaviors. Well, humans are not ideal reasoners. Well, just a nice quote of Sir Isaac Newton, who lost once a lot of money at the stock market. And he was saying, I can calculate the movements of the heavenly bodies, but not the madness of the people. No? So this is something which unfortunately comes into play here. And, well, one needs skill and expertise. No? So in order to really solve large-scale, say, configuration problems or optimization problems, one must know the tools very well, and there is quite some learning and training that one has to invest into that. No? So for the future development of AI, no? So regarding that, no? Well, we might not have a strong AI that we really build systems that model human reasoning as such, that weak AI, where we're just building systems that are mimicking these capabilities would be good enough, but still we need to reason about the models that we are building. No? We would like to see that actually we have, also from the perspective of symbolic AI, the possibility to address more problems, that we have a broad AI that is able to deal with multiple problems. No? Neither symbolic AI nor sub-symbolic AI alone, no, in my opinion, will be sufficient for that. What large language models can do in this regard is debatable, so to say. I just refer here to Jan LeCun, who was at AAA, a major conference this year, be very skeptical about that and saying that this could be a dead end. In the end, so I think what will be important is to bridge symbolic and sub-symbolic AI, so that we need mental faculties in order to have advanced capabilities of systems is something that people agree, but the way how this should be achieved is something where people have diverging opinions. Neurosymbolic AI, and I think you will hear more about that than in the talk by Frank, is one of the directions for that. What in any case will be important is that we will need system architectures which are combining, so to say, different modules with different capabilities. Okay, thank you.
Thank you very much, Thomas. So now please if our responders can come to the stage. So I will not waste time on long introductions. We have two colleagues, Martina Seidl from the Johannes Kepler University of Linz, who has contributed extensively to symbolic AI, mostly by making logical reasoning effective, by making it working on solvers. Martina has wonderful contributions in that direction. And our colleague Alexander Schindler from the Austrian Institute of Technology has a very different expertise, not so much logical reasoning, because he actually works on multimodal AI, audio analysis, music information retrieval, and I have absolutely no idea whether one could ever use any type of logical reasoning. How would we use logical reasoning there? It's not the strongest technique, right? So we look forward to your contrasting viewpoints. Who goes first?
Okay, thank you very much for the nice introduction. Also, thank you very much for inviting me, and Thomas, thank you very much for the very nice overview talk. When I talk about symbolic AI, so I'm head of the Institute for Symbolic AI in Linz. I'm basically referring to computational logic. So there are different streams in symbolic AI and different directions, and I'm doing computational logic, and I think this is an exciting field for several reasons. But there are 2 points I want to emphasize, and we already heard them also in the talk of Thomas. Traditionally, logic can be done or seen as a pen and paper subject, but when we do computational logic, we have very efficient tools to actually solve problems. Yeah? And the two advantages I see when we use computational logic approaches like SAT solving or extensions is that on the one hand, we get a concise formalization of the problem we are considering. And when talking, for example, about configuration problems, this is not obvious at first hand. One would think, for example, when a company has done the configurations of machines for several years, they know what they're doing, but actually when it then comes to using logical method, it turns out that they often do not really know what they're doing because they forgot to consider certain cases. Yeah? And when we do the logical encoding, we see what was forgotten, where are the semantic gaps. So with logic, we get a clear and concise representation and understanding of the problem we are considering. Yeah, this is the first point. I see logic as a specification language with a very clear semantics that help us to understand problems. And the second thing is the reasoning aspect. Yeah, so if we have formalized a problem, we can solve very interesting tasks in a simple way. And this is also what we give to our students. Yeah, so we're teaching in Linz logic in the first semester, and after 3 lectures, they're able to build a tool that solves Sudokus. Yeah? So this is really easy. When you have logic at hand, when you have the tool set, you can very quickly solve complicated search problems. And often I'm confronted with the question, but isn't this really used in practice? We're not hearing about symbolic techniques in the media in a large scale, except there are success stories like the Pythagorean triple, or sometimes symbolic techniques also. That there was a success story. This was another field of symbolic AI where DeepMind was beaten by some colleagues from Linz who are doing computer algebra. But usually symbolic techniques are not so much in the press, but it's in the background somehow. And this is also mentioned by Thomas when we talk about verification problems. Then these are not something that is just done in the labs of universities, but this is something that is really done by huge companies. And currently all of the big players in software and hardware are investigating a lot in symbolic techniques in order to get their complex systems right. So logic helps to deal with complexity and to deal with to deal in an exact manner, again in a concise manner with complexity. And what is also not, and now I'm coming a bit to the trade-offs. What is really a challenge in the symbolic technology is this engineering aspect. On the one hand, on the encoding level, and on the other hand, on the engineering of the solvers. So the solvers that work efficiently are extremely complicated, and the question is now, how can we trust these solvers? And when we think about SAT, so this is a very old problem when we want to decide a propositional formula. And one would assume that everything from the theoretical side and from the engineering side is clear, but this is actually not the case. Yeah? So at the moment there is a lot of exciting developments that deal with how to prove the correctness of the result of a SAT solver. Yeah, so usually the SAT solvers are, because of the complexity of the engineering, not verified tools, but we need to ensure that the tool that verifies other tools has to be correct, even though this one is not verifiable. Yeah? And this is what is ongoing in current research in SAT solving, and this is a very important topic currently. And here, there are also a lot of opportunities. This is what I wanted to point out in this regard. Finally, about the engineering aspect regarding the encodings. Yeah, so one has to really know how to write down a formula. When we think about propositional logic, we have only Boolean variables and some logical connectives, and this is very like going down to assembly language. We have then more advanced logics like SMT, which was also mentioned, where we then have background theories that makes the modeling easier, but still a lot of expert knowledge is needed. And here I see a huge potential where LLMs and modern machine learning techniques can help. And I'm excited in the bilateral AI, in the cluster of excellence, to excite opportunities for bringing the fields together. Thank you.
Yes, thank you for making it so exciting. Yes, I have a machine learning background, and additionally I'm coming from applied research. So usually in such scientific events I'm sounding too applied. And on the other hand, on industrial events I'm sounding too scientific. But usually I sound more like a salesperson. So what can I share with you? Maybe I can share with you the story how a machine learning guy like me came to the decision to hire PhD students with a semantic AI background, to give them space and budget to pursue their research, and to encourage them to create their own little research field, which has now turned out into our Symbolic AI research group in our competence unit. Back then it started problems that I had in projects with law enforcement agencies, that we needed to analyze multimodal video content. I was tasked to identify gunshots, explosions. A colleague identified some visual concepts. And later on, we needed to combine this with textual information like named entities. And this was really a task, and this multimodal fusion worked best by applying semantic context, like projecting everything into a graph presentation, a labeled property graph. Later on, we tried graph neural networks on top of this to make some downstream inference and so on. So this was my first contact with this. But later on, with building now very kind of successful NLP team, we figured out that in some occasions we cannot just rely on machine learning, we cannot just rely on large language models, and we need to find some additional information to infuse this. And then came ChatGPT, and you probably know all the advantages of ChatGPT and large language models, but could you also tell me one of the biggest disadvantages of ChatGPT? Energy is a good one, but the one that I'm in applied research mostly confronted with is that now non-tech people are experts in AI. I'm sitting in front of CEO and they tell me, oh, we have this brain drain of retiring experts, and can't we just create, we have everything documented in our QM documents, can't we just create an expert digital twin? And then he continues, yeah, it's no problem, I've just tried it yesterday using ChatGPT with one document, it works perfectly. And then it goes, and then we try to explain, oh, it's difficult, but this SME this just said, okay, maybe if it's not possible, RAG, what's RAG? This is something good. And if you all know about retrieval augmented generation, but in a nutshell, you bypass the disadvantage that it's really difficult to get new knowledge into a large language model, especially domain knowledge from local documents, by just adding a retrieval system where you embed all the documents into text vectors, and then you do nearest neighbor search, and you hope that the retrieved result set has a good enough quality to pass this on to a large language model to generate a satisfying answer. The problem is, for the last 20 years, I've been waiting for qualitative retrieval results in vain. The quality of this is still not good enough. So you need to augment the augmented system again. And here, knowledge graphs, symbolic AI systems are crucial. You need to have some document understanding. You need to have some domain expertise. And usually companies have those expertise. They are not sitting on the documents and now identifying, oh, I can use these documents. No, they've been dealing with these problems for years or for decades. They have created their own approach to this. They have introduced taxonomies. They have spent a lot of time into adding dictionaries for filtering content and so on and so on. This is a lot of manual work, this is a lot of effort, and this has value, and you can use this knowledge and introduce it into the system. And through augmenting this, you get much better results. The systems are now more informed. And the newest trends in AI, agent-based systems, where you kind of push the responsibility for taking automated decisions to a large language model, it is much more relevant to give constraints, to give guidance, and you cannot just rely on the large language models to give very critical decisions. And this is also one of the components where we in our applied projects use symbolic AI, use semantic technologies to give additional context, to give additional guidance, and to give more reliance and trustworthiness into these systems.
Thank you very much, Alexander. An interesting personally. So, Thomas, do you want to say something before we go to the audience?
Well, I just want to comment on this problem that you mentioned, so that experts are retiring and now that knowledge should be captured in a system. This is not something new, actually, and it has been done over and over again. And as an anecdote, I remember that we at the TU 30 years ago had such a project with a professor in electrical engineering who was an expert on micro switches. So the idea was to capture, when he was retiring, his knowledge in an expert system so that this could be later used. But the project utterly failed for the very reason that many things that were not captured by the systems were just trivial to him. He always said, oh, that's trivial. So I mean, this is the real difficult thing. And this might also be in your company. Not all of the information is in the documents. Very often so that there is extra knowledge, and to elicit this knowledge and to capture that knowledge is a challenge. In the 80s, when the booming days of expert systems there was the profession of they call it knowledge engineer. There were processes described of how this knowledge should be elicited and so on. And maybe, we are coming back somehow to that. Now that there is more opportunity, and more machinery in order for building these knowledge-supported systems, that is certainly interesting. And as for ChatGPT and these large language models, as you said, we cannot trust them because they're hallucinating, they are producing something which is likely, according to their prediction, but you have to check always. It would be great if you would be able to have advanced versions of these systems who have the knowledge about tools, that they could use certain tools in an appropriate way, be it a SAT solver, be it a reason of a knowledge graph, in order then to come up, or a planner to come up with the respective solution to a problem they are given to. But this requires to have meta-reasoning properties, to understand about capabilities of other systems. And this is something we will have to do, or that would be great to do.
Thank you, Thomas. I very much agree. Questions, rebuttals, comments from the audience? Francesco. Sorry.
Francesco, Free University of Bolzano. Thomas, thank you for your presentation. It was very, very interesting, and you gave us an account of what symbolic methods can do. And I agree with you about all these success stories. But the reality, I would say that in the last 20 years, a lot of tasks that were solved effectively with symbolic methods have now been addressed with sub-symbolic methods. Think about natural language processing. When I started doing AI, nobody was thinking to do natural language processing with neural networks. Now it's the opposite. Nobody is doing natural language processing. Even in recommender system, which is my field, I started building a case-based reasoning system to solve a recommendation task, and now nobody is using this type of approaches, and then again neural networks. So the reality is that we are moving towards step by step on that. So my question is, from your point of view, which are the areas where symbolic reasoning is still strong, but there is the risk that the sub-symbolic methods will in the future become effective? Even in verification, do you really think that it is not possible at all to do verification in the future, not now? So we agree with the sub-symbolic methods. That's the provocative question that I have.
Well, it's a bit a provocative question, so to say, but well, I believe in the end what these neurosymbolic systems would have to do is semantically nothing else than what the current logic-based methods will have to do. Especially if you want to have absolute truth, then you have a search space that you have to to go through. Now, I'm not sure now whether with probabilistic methods nor these things it will be possible to do that. No? So this is just my view, no, so to say, on that. No? I mean, we should not forget that these systems, no, are systems based on uncertainty. No? And I mean, they make predictions. No? But there is no absolute certainty. There's no absolute truth. No? If it comes to probabilistic arguments, quantitative arguments, then perhaps yes. No? Still, the issue, no, of transparency and of understandability of how these things come about, no, will be in the room then. No? I mean, as for language processing, I agree. I mean, one should not try to use symbolic methods if in the end, I mean, it doesn't work out, no, and other methods are better. No? It's clear, but I mean, so if we are talking about configuration, no, if we have systems, technical systems like chips, no, where you really want to be sure that the chip is working correctly, then I think logic-based methods and with their capabilities of being executable specifications will be important.
May I also give an answer?
I
Okay.
I very much suppose so, yes.
There are big issues currently concerning computational complexity and processing time. So if you want to analyze a lot of data, pushing everything onto large language models is outrageously slow. Even now with the trends to small language models, they're still slow. So if you have a combination, an opportunity to make things faster, like having some knowledge already protected in the knowledge graph, this will speed things up massively. And for many things like identifying changes in documents, people are pushing this to LLMs and say, has this paragraph been changed? You can do this with edit distance or anything else, and it's much faster. So you need to take some trade-offs where you need speed or whether you need this complex reasoning from large language models. And as long as we don't solve these computational complexity and consuming issues, I think hybrid approaches are the best way to go.
Yeah, again, Enrico Nardelli. I would like to comment on what Francesco said about the advantages of sub-symbolic AI in processing data in language processing and vision. Which is true that, I mean, to do the basic analysis of raw data, these approaches are much better. But then when it comes to reasoning or understanding the meaning of what's in them, then I would say that we still need symbolic representation. As Thomas has shown with the example of the chessboard covering, it's clear from the answer that the machine has no real understanding in human sense. And I mean, if we start discussing the term understanding, we may stay the entire day, but still, it is clear that, and there is a very recent paper by the team working at Apple that has analyzed a lot of variation of these problems, showing very clearly that when you start variating a problem, changing some element of the domain, then the machine, I mean, doesn't do a very good job. That's why I think that we still need symbolic and we still need to integrate. I don't know how, but we need an integration of the two things. I'll stop.
Look.
Yeah, I want to come back to a point that Linda already raised, which is the preservation of knowledge about symbolic techniques. Because you know, I see now many people graduating who haven't the faintest idea about symbolic methods and believe that, you know, this is, well, of course, encouraged by people like Hinton who make that kind of statements that, you know, it's all the symbolic stuff is old-fashioned. This is a word they like to use. Well, sometimes you add good old-fashioned, but basically what remains is old-fashioned. So this is a stigmatization of, you know, these kinds of approaches. And so I don't know whether the panel sees the same kind of thing, and also what we could do about this.
Yeah. Yeah, so I totally agree. So I also see this stigmatization of the symbolic techniques. And I think what we can do is we need to show the people that these techniques really have applications and that they can do something what they can understand. I mean, it depends on what level you want to explain. There is a more general audience, yeah. And if you come to them with mathematical formulas, they will say, "Oh, I hate maths," and they will shut down everything. But if you come with logical puzzles, with games like Sudoku, and explain the concepts behind them, you get very far. And this is also something I do in my outreach activities. I have a game which explains reasoning on propositional logic on a CNF level, and people like this. They have to solve some coloring problem. They come up with techniques like unit propagation, like pure literal elimination. They invent them by themselves, and they understand what is happening. And when they have this understanding, one can explain, yeah, okay, this we can use for verifying systems, because solving a planning problem is nothing else than a verification problem. Yeah, and so on a general audience level, this works very well. When it comes to computer science students, and especially people who are studying AI, so the AI students, they are very skeptical, because nowadays they mainly come for the machine learning. But here it helps to show them that we have the good tools and that we can do the encodings very easily. Yeah, so that when they want to solve certain problems, we can directly give the problem description to a tool without complicated programming, and I think this also helps a lot. But we have to show and express in the right manner and talk to the people.
Since you are all in favor of logic, I have now a provocative question. How do you explain the success of this machine learning approach? How do you explain the success of LLMs? How do you explain where everybody's speaking about it? Is it just a sales argument? Is it the media, or is it the big five who are investing in that? Or do you see serious limits in a logic approach? I just want to mention knowledge and engineering, you mentioned. Search space. Exploding facts or exploding rules you need for really describing large word problems. So I'm just wondering, because we are talking about a paradigm shift. We see it. We see that students are moving into other directions. So just an explanation from your side.
Yeah, so I see it mainly coming from the fact that for machine learning we have a lot of applications that people have in their daily life. Yeah, so they want to use their phone, they want to do advanced tasks with their phone, then they see, okay, this can be done with machine learning. Regarding symbolic technologies, usually people don't solve verification problems. They don't have scheduling problems, what they have to solve at home. And I think this comes from the wide range of popularity.
I think it's the accessibility. So we move completely away from computer science. It's a chatbot. You can talk with this chatbot in natural language. Prompting is something that even my grandmother can maybe learn, but my mother has already learned it. And you don't need any mathematical, technical, or any background, and you can create AI systems. I think that's one of the reasons.
Well, yeah, agreed. No, I mean, but this is especially among computer scientists an interesting observation, because just for solving Sudokus, I know it from teaching, from different experiences. You have the students who are sitting down and they are writing then a program. For doing this, I didn't have a student yet who was coming up with a neural network for solving Sudoku. But I mean, usually the program, they do not look around. They're not aware that there are tools. The smarter students are. They at least do a web search and see there is a tool. I just write 2 or 3 lines of code in that declarative language, and then I get the solution. And then actually I can vary the problem and get solutions like hint generation, that you have the smallest number that you put in a Sudoku and as a template, such that you still have a unique solution, and all of these things. in many cases it's awareness, no? But there is also problems where symbolic methods are not really appropriate. No? If you have because it's complex function fitting that you're doing, no, in some way. No? And for that, no, logic-based methods will simply not be suitable. There's nothing to say about that. No? But on the other hand, you will not be able to do everything with that. No? That's the thing. No?
Sorry to speak again. I think the economical side is highly important. This company have been investing $10 of billion of dollars in developing these systems, and they are pushing at media level, and everybody reads about this, and everybody want to try them. So I would not undervalue this economical side of the thing. And of course, most of people, they just see a machine speaking like a human beings, so they project intelligence onto the machine, even if, I mean, then they discover that it's bullshit. So it's I think this economical aspect is highly important, and we only have to wait and see. I would say 1 more month. I mean, next DGUM workshop, we will see how the things will be. Maybe in some fields there will be a real business case. It's not yet there. That's what I don't yet see the money coming back after the investment. You know, if you have invested $10 or $20 billion, then you want some of your money back.
I don't know if the moderator is allowed to comment, but I also want, you raised something that I actually think is quite important. The type of intelligence, the type of things that these systems can do, fool us very easily, right? When you have a system that can give you a chocolate cake recipe with similar language to the one used by Shakespeare, that impresses us as humans, it fools us. And we already saw that since the Eliza times in the 70s. This is the same kind of, they have abilities that surprise us, and the media hype makes it very easy to believe that they're super intelligent. I think people are far less aware of what the systems cannot do than of what they can do, because people don't use them for solving complex problems, for several step reasoning, when large language models still fail miserably. For planning, symbolic techniques are still vastly superior. So I think that is an important factor that, and there is this wishful thinking, like, cool, there is a super intelligent machine, maybe it can solve all my problems, and little awareness of the things that it cannot do, rather than an intrinsic failure of symbolic methods to solve problems, which is. Can I also ask a question, Thomas? And it's related to what you said. You still had this kind of scalability and exploding search space as a limitation of symbolic AI. But Alexander actually mentioned it as a limitation of machine learning on large scale, right? I mean, how much is it really an obstacle, given how much computing power we have, but also how our techniques for reasoning have improved, how we have gone better at, for example, even if the problem is untractable, to compile it offline into tractable representation. Is it really a major obstacle, the scalability still? Because if we take into account the training, let's be honest, symbolic AI is way cheaper than large language models, right?
So you mean for online solving problems, no? Well, I mean, in practice, it's still an issue. No? The configuration experts here in the room will agree to that. No? That if you really have to deal with very large instances, no? then also the best and smartest methods alone, out of the box, are not sufficient. Unfortunately, no? Combinatorics is a beast. No? This is what it is. No? So, you need skills, expertise, no, and ad hoc methods in some cases, and then in order to solve that. So there is nothing you can do about that. No?
Yeah, but machine learning is also pretty expensive, right? I mean, training ChatGPT took a lot.
Well, currently it is. No? So, I mean, we have the choice between burning our planet with Bitcoin or with with the current machine learning models, even though, I mean, there is work underway to make it much more efficient. And this is important. I mean, think back what happened in genomics for DNA analysis when Craig Venter was coming up with the first methods and tools. That was in the 90s for sequencing the human genome. That was a huge effort, very expensive to do, and required quite some resources. And nowadays it's daily routine. I mean, there's certainly huge potential for improvement. I mean, remember what I told, what I presented about libratus and pluribus. Coming up with better methods, doing it smarter, might give huge computational benefits and energy benefits. And I mean, if you think about playing poker, I mean, how much energy is our brain consuming? So I'm not, how much? But 10 watt, 20 watt against a supercomputer or a GPU. That I don't know how many, 6,000 watt or whatever, just a couple of GPUs. These are the big issues then also, so in addition to advancing the capabilities of the systems.
We have two, Frank, and well, maybe here and then Frank, or vice versa.
Oh,
okay.
So hi, Gerd Friedrich once again. So I think the question of Vienna is really important. And so I think it boils down to the question, why is Microsoft, for example, investing billions in large language model? And I asked this question to a Microsoft manager, and somehow you have to follow the money. Yeah. So the big question is, what are the cash cows of Microsoft? And Microsoft simply wants to make sure that these cash cows are producing even more cash by applying large language models, and so by question answering, by enhancing documents and so on. Yeah, so they build in all these large language models, yeah, into the products in order to make them even better, yeah, and to get some of the money back from Google, yeah, because now people are using more their, for example, tools to write documents and so on. Okay, so and we have to say, I'm on the symbolic side. We have to accept the fact that this guy on the machine learning sub-symbolic side can do things we can't do, yeah, and Microsoft is spending money on them, yeah. I think that this is. I'm not sure if this is the correct answer, yeah, but I think this is an explanation why they are doing this.
Frank? Here. Next one.
Hi, Frank van Armelen from Amsterdam. Luke's comment very early this morning was to not create this antagonism. And I think that's exactly what we are doing here. Right? So, and I think that's not a very productive attitude. I think the attitude is not us versus them. The attitude should be which part is good at, which trick is good at which problem. And I don't think the answer is universal yes for either side. So I think that's where the real challenge is. That's my first comment. Second comment is we should be a little bit more aggressive in using computational power. So in symbolic AI, we still read papers where they said, oh, well, here's my performance table and I couldn't run this problem because it timed out after 6 hours on my laptop. Right? I mean, at the machine learning conference, they laugh at that for the right reason, right? So they run on Amazon Web Services. They run 50 GPUs. They run them for 2 weeks. Okay, what would happen with our techniques if we would do that? So I think there are lessons we can learn from them. Part of the bitter lesson of Rick Sutton is things scale with compute, right? And it's not just sub-symbolic techniques that scale with compute. We do so. I think we should stop this antagonism. We should really find out where the boundaries are between the two. And I think we should be a bit more aggressive in throwing comparable amounts of compute at our problems and then see what happens. Does that make any sense?
If I may give an example which comes to my mind is we've been collaborating with companies like the semantic web companies or OnLim. They're developing knowledge systems where they have kind of a complex network of agents, and they're routing the request through these agents, and the agents decide whether to route this to the knowledge graph or to the LLM, but also intermediately as kind of route back and forth and so on. And the answer is then a combination of an LLM-generated answer, which is then infused with links into the knowledge graph. So you have this combined answer, which gives you a correct answer to your question, but also links into the enterprise knowledge system. And I think this is a good example for such things.
Mm-hmm. I mean, if I can comment, I mean, you're right, Frank. No? I mean, one also has to take into account that complexity requirements and the computational cost requirements of problems that we have in computational logic are quite well understood. There are sweet spots of problems that can be solved with faster with the use of massive use of hardware, parallelizable problems, which are linked to classes of logics that have been developed for just that purpose. But very often this is then not highly respected, because then the people say, well, I mean, this is rather simple, what you are doing. The more challenging things are actually problems that cannot be that easily parallelized, that with many GPUs or multi-cores, it's not so easy to do that. So this is theoretically known. So this is also what do you expect, and what is the level of, so to say, intelligence, or where the use of logic and logic-based methods comes in. So this is something that one has to take also into account. And I mean, it already, I mean, would be good if logic-based methods, not at the full scale of the capability of the formalism, would not be discredited. Of saying, yeah, you are solving things that are not so difficult, but still there are the aspects of understandability, of having a model, being able to analyze the things and more easily to generate explanations that people can understand. Perhaps this also helps to shift the view a bit in this direction.
And additionally, we've been mostly talking about like knowledge-based systems or chatbot systems, but if you go into the dependable systems, autonomous systems, you want to have reliability, you want to have precision, you want to minimize the risk of probabilistic effects as much as possible. And I think this is where semantic AI, symbolic AI systems have the best applicability to give you the reliability, the trust, the guidance. Maybe you can use some vision language models for better segmentation to give input into the systems, but you need to put constraints so that accidents are avoided and yeah, to give trust.
My name is Georg Malek. I'm not active in academics. And my question is, do you see a role of quantum computing in symbolic AI? Spoke about NP problems and such things, and
that's an interesting question. So in that regard, I'm not 100% sure. I mean, it depends, because also this quantum technology, the whole is based on probabilities. Then in the end, and these things. I mean, if you want to have certainty, then whether this is absolute certainty, whether this will work, I don't know. So in that regard, if you want to live with probabilities that are good enough in practice, then perhaps yes, because I mean, as we know, or at least for computing machinery, because we know that you might have hardware failures, that just from radiation, natural radiation, are in the area of 10 to the minus 15 or whatever, very unlikely to occur, but it may happen. So if you can push down probabilities to that level, you might be fine with that. But in general, I'm not sure. So that. Now, I'm not sure whether, because there is very often people say you can solve NP-complete problems now with quantum technology. But I think that's not really correct. One has to very closely look into what you're talking about.
Can I? Can I quickly? Yeah, but there are works that go in the other direction. So there are a couple of approaches that use symbolic technologies to improve quantum computing designs. Yeah, so which optimize quantum circuits or which, yeah, help to get them right. So we can also help there.
Thomas?
So interest in generative AI has very much been driven by the systematic deployment of rhetoric and promises by the leaders of companies like OpenAI and Google's DeepMind and so on, that AGI is something that their technology is poised to accomplish within specific timelines of 3 years or 5 years or 7 years. You know, they argue about those things and that will have these profound impacts for humanity. And of course, back in the early days, Minsky and McCarthy and their colleagues made similar promises and offered similar timelines. I think the last time Symbolic AI made a serious push in that direction was probably Lynat's Psych project in the 80s. And it seemed that the rhetoric of AI professionally shifted much more towards we will take knowledge and do things with it that make computers more usable versus we are on a glide path to superhuman intelligence. So, I mean, we may not believe them, but we know what Sam Altman says we will get if we give him that $7 trillion that he's trying to raise from sovereign wealth funds. If someone gave $1 trillion to Symbolic AI, what would we get? What's the dream of Symbolic AI at this point? And I actually heard that same thing about the SAT solvers from Donald Knuth, who told me that that work had really been kind of useful more generally. And so I see how Symbolic AI and logic have been integrating very productively into computer science more generally. But does Symbolic AI still have a claim that it can do something really big if it gets the resources?
Thomas, you go for it.
Well, I mean that's a tough question to answer. No, I'm not sure actually about and whether making yet another big promises that cannot be kept would be a good thing to do. No? What I think would be reasonable is just to see that the technology can be pushed to a level that use is created in systems in cooperation with other systems. It will not be that you can solve all problems with that, but there will be components in systems where reasoning modules are just used for different issues, like bit planning, like these optimization problems, or decision making and so on. But I mean, to be the solution for AGI, I don't think that one should promise that. So I would be cautious in not making overselling claims of what one can do. To be.
There are enough people doing that already, right? Yeah. I guess the crowd is getting hungry, but we have one more question at the back.
Okay, so my name is Erik. I'm a startup founder in the space, and we work with human-centered technology. But I was just wanting to follow up and give some insights to Microsoft's reason to invest in LLM. It's a big company like that. They will be thinking of it from a financial standpoint. And I just came back from a conference with impact investors talking about purpose economy. And they had some interesting insights into this logic. So you go and you invest in something, and you don't expect the outcome to come, or the value, the money to come back from where you invest, but from the impact it has on your ecosystem. So in Microsoft's case, we already see it in their Office pack everywhere. They are kind of sprinkling LLM to optimize the user experience, and they can then take more payment. So they're getting their return from other places than the initial investment. So I think it's important to remember that when we try to invent new stuff, it doesn't always come, the income doesn't always come from where you're inventing. And I think also I just want to follow up quickly on Frank's comment here, because I think it's really important to avoid what we have started to call utopia fallacy. So you always start measuring against the end goal that is utopian, and you forget that the small steps are actually bringing value here and now And that's still progress. I think just on Alexander's point, we are doing a lot of similar stuff. And I think it's extremely important, the point that you were making on how you how the LLMs are actually making technology more accessible. So we are working with projects in Africa, in very poor countries. And what we see is that what LLM is bringing is actually making technology available to them. So it's extremely efficient in transforming basic economies, which you can't do today with the traditional approaches. So I think that's some of the important things to bring into the conversation, especially since we're here with digital humanism, not forgetting why we are here, right? So just some reflections.
Thank you. Well, does any of you want to add something to that comment before we go for lunch? Because I think people are getting hungry.
Yeah, maybe just emphasizing on this point, even AI agents now are the new hype, and they might seem complicated, but there are already tools where you can drag and drop AI agents onto a canvas and give it a description to the natural language description to this agent. You can connect them visually. Anybody can understand this and program these agents in natural language. So it really has become very accessible and easy to approach for non-technology related people, yes. Thank you for this feedback.
Okay, so thank you everybody. Let's thank our speakers. And let's go and get lunch.